So in last session, we learned about TLP assembly and we also learned about PCIe topology. We also talked about uh, posted and non-posted transactions. So let us start with a overview of how does TLP packet disassembly happens in PCI Express. So TLP is received. So it goes through several steps of assembly with different layers adding bits as I show you in last session how the assembly happened. So it add different layers to it and fields and it adds various fields for error checking. So do anyone remember what error checking methods I talked about in last session? So this is a live session, so we will keep it interactive as much as possible. So do anyone remember error checking protocols which we talked about in last session? So do you remember the ECRC and LCRC protocol which we talked about in
LCRC.
class? Is anyone speaking? Should I repeat what were the error checking protocols?
Yes, please.
Okay, so the transaction layer at the ECRC at the end of the packet, as you can see here. Is my screen visible to you all? Can you see this? What is shown here? It is the structure of
Yes.
TLP layer. So this is the ECRC. So this is the type of error correction code that ensures that no error occurs during transmission between the sender and receiver. And this is LCRC, you can see here. Is it visible to you all? So we were on ECRC and LCRC. So now everything is visible, right? So let us start. So the data link layer also adds another checking code called as LCRC as it is visible here. So this code allows receiving the device to check if any error occurred during transmission over the specific link. So if there's an error, the receiver notifies the sender and the packet is retransmitted. So when we already have one error checking protocol, do anyone have idea that why we are using two protocols for checking the error? Any idea? Would anyone like to give a guess for this? So LCRC only checks for error on the link between two neighboring devices, whereas ECRC, on the other hand, checks for error on the entire path from the sender to the final destination. So this is useful because error could happen inside the devices like switches or ports and and that route the packet. So LCRC won't catch those. So that is why we need one extra error checking method called as ECRC. So do you have any doubt in this? So let us now move to TLP disassembly. So disassembly process is when the receiving device reverses these steps. So the steps which are taught in TLP packet assembly, so they are reverse in the TLP disassembly. So So let us learn that how physical layer strips off the transmission bit. So when the receiving devices sees the incoming TLP packet, the physical layer is the first to handle it. So the physical layer checks for special characters like the start and end characters. So that is where we are. So that is that were added during the transmission. So these characters tell the receiver where where the packet begins and ends. So after verifying these control characters, the physical layer removes them and forwards the rest of the packet to the next layer, which is the data link layer. So let us understand how the data link layer process this. So data link layer is responsible for ensuring packet arrive without errors. So it has two types. It does this checking using two methods called as LCRC. LCRC is link cyclic redundancy check. So this checks for transmission error between the neighboring devices, that is on the PCIe link. And second method is it checks the sequence number to ensure the packets are in the right order. So if there are no errors, the data link layer remove the LCRC as you can see here, and it removes the LCRC and sequence number fields. So which are added for error detection and passes the remaining packet to the transaction layer. So, how does transaction layer process after this? So, it now works on the core part of the packet, which includes the header, data, and possibly the ECRC field. So, if the receiving device is a switch, so it will check the header to see where the packet should go. So a switch, i- so a switch is just like a traffic controller. It looks at the header of the TLP to see where the packet is headed. So the switch does not modify the ECRC, but it can check for errors and report them if needed. So if the receiving device is the target, it checks the ECRC to ensure there was no error in the packet's journey across all the links and devices. And the final step in the disassembly is the forwarding the core information. So when the ECRC, if it is present, it is checked, and if there are no errors, the transaction layer removes the ECRC field. So what's left? The header and the data, which are then passed up to the software layer of the device. So the software layer is where device process the request or data that was originally sent. So do you have any doubt in this? So let us now understand the non-posted transactions. So yesterday we learned about non-posted transactions. Would anyone like to uh, tell that what happens in non-posted transactions? So a non-posted transaction means that when a request is sent, the sender waits for a response. So this is commonly used in read operations, where a device requests data from memory and expect a response with the data. So let us understand with the help of this diagram. So a endpoint, as you can see, we have a endpoint here. So which wants to read data from the system memory, which is here, and it sends a memory read request. So memory read request is depicted with MRD here. So this request includes a target address which tells the system where the memory is located. Now, how the routing of the request happen. So the request travels through the PCIe system, passing through the switches. As you can see here, we have switch A and switch B. So the the request travels to it through these switches to the correct destination. So in this example, the root complex recognizes that the request is for the system memory. And then how does the fetching of the data happens? So the root complex reads the memory at the at the requested address and gathers the data to be sent back to the endpoint. Now sending the data back. So the root complex sends the data back to the endpoint in completion data packets. So here CPID is the completion data packets. So if a lot of data is requested, then multiple completion packets may be sent. For example, a large data read might require several packets as PCIe allows maximum of 4 KB of data per packet. So how does the data find its way back? So it uses the BDF number. So we will learn about BDF in more detail in the configuration chapter. So so for now we can understand we use the BDF number for finding the right parts. So additionally, the request also had a tag. So each request is given a unique tag to help the endpoint match the incoming completion packets with the correct request, especially when multiple requests are being handled simultaneously. Now, handling errors. So, if an error occurs, the completer or the device which is responding to the request can indicate this by settling specific bits in the completion status fields of the packet. So, this lets the endpoint know something went wrong. To Though how to handle such errors depends on the software, not the PCIe specifications. So now let us understand a special case of this, which is locked reads. So what is the purpose of this? So this is a special case where a processor needs to ensure that no other device can access or modify a specific piece of memory while it is performing a critical operation. So this is mainly used for operations like atomic modify write, which are essential in tasks that are managing a semaphore. So what do you mean by semaphore? Anyone would like to answer? So semaphore is a variable that controls access to a shared resource. So here is how the log. So let us understand how the log reads work. So, first of all, let us talk about atomic operations. So, imagine you have a semaphore, a variable that prevents multiple devices from using the same resource at the same time. So, when a processor checks the semaphore, like testing if a resource is free, and decides to change its value, like marking the resource as in use, so no other processor should be able to modify the semaphore during the process. So to ensure this the processor locks the memory location containing the semaphore. So this prevents other devices from accessing or modifying it until lock is released. Now let us understand about race conditions. So without locking, two processor could try to modify the semaphore at the same time, leading to a race condition. which could cause unpredictable results. So, the lock ensures that one processor completes its operation before another one can access the memory. So, how lock reads happen in PCIe? So, processor sends a locked memory read request, which is shown here. This MRDLK is the locked memory read request to a specific memory address. So this request travel through PCI system through switches. As you can see, here is a switch and other routing devices. Eventually reaching the memory or device where the data is stored. So now let us understand how locking the path happens. So as the request passes through each routing device like switches, so the port gets locked. So this means no other packet can pass through the port until the lock transaction is completed. Next, when the memory device receives the locked request, it fetches the data and sends it back in a locked completion packet. So where is the lock completion packet here? So this is CPLDK. Here is the locked completion packet. So the completion packet travels back to the original requester and the ports unlock as the packet passes through them. So now how does this locked reads handle the errors? So if something goes wrong, like the data cannot be fetched, the device sends a locked completion without data indicating an error. So the status field in this completion packet will tell the requester what went wrong and the lock will be cancelled. After that, software will need to decide how to handle the error, for example, by retrying the request or taking some other action. So let us now discuss IO and configuration rights in PCIe. So in computer systems, IO write transactions are a way for a processor to send a data to a specific device, or we can say it as endpoint. So these transactions follow specific rules. So let us understand the rules. So first step, the targeting the legacy endpoint. So an IO write can only be sent to a device designed to work with this type of communication. So, routing the request to the data travels through a network of switches based on IO address until it reaches the target device. Then, on a target device, once the target device receives the data, it sends back a confirmation message to the processor. The confirmation does not contain any data, it is just a status field indicating whether everything went okay or if there was an error. So, if an error occurred, the processor software is responsible for fixing it. So the confirmation tells the processor that the data has been successfully delivered. Only after receiving the confirmation can the processor move to the next. So the processor can move to the next instruction. So this is the key difference between a non-posted write and other types of writes. So in non-posted write, so the processor must wait for the confirmation before continuing. Then in memory write, the processor does not wait. It assumes the data will eventually get right. So why wait? So waiting ensures that the next operation that is depending on the success that does not happen too soon, avoiding errors. So only the processor can initialize non-posted write because it is closely involved coordinating the critical steps. So let us now discuss the quality of service in PCIe. So quality of service in PCIe ensures that time sensitive data like audio, video streams is delivered on time while still supporting less urgent data like file transfer here. So let us understand with the help of example. So let us take a problem. So uh, a camera data, so it needs to arrive on time or the video will become choppy or lose frames. And next we have another uh, function also which we need to do, that is file transfer data. So we so it does not care how much timing, it does not care much about timing, it just needs to arrive without errors. So QoS ensure that the video data gets priority, so it arrives over time even the system is busy. So so let us understand so how QoS works. So priority level, so each packet of the data is given a priority level by the software using a 3-bit field called the traffic class, and it have higher number. So higher number means higher priority. Each port in system has multiple lanes or buffers to handle different priority packets. Packets are placed into right buffer based on the traffic class. So when there are multiple packets ready to be sent, the system uses rules to decide which packet to send first on priority. So, in addition to managing buffers, the system also decides which input port access to an output port when multiple ports complete for resources. So, this can be handled by the hardware or software. So, with these mechanism in place, the system can guarantee the high priority data like video gets enough bandwidth and low latency, ensuring smooth performance. So, do you have any doubt in anything in this? How QoS works? How quality of service works? So, let us understand quality of service with the help of this diagram. So, a video camera is streaming live footage to memory, and a hard drive is also sending backup data to memory. So, what happens without QoS? So, both devices compete for the same bandwidth. So, if the video does not get enough bandwidth, frames are dropped and the video looks choppy. So, what improvement happens with the QoS? So, the video packets are given a higher priority, or you can say a higher traffic class. So the system ensures the camera gets enough bandwidth and fast delivery, while S while the other data waits if needed. So the video stays smooth and the backup still complete. So, what are the benefits of having QoS? First, we have the advantage of prioritization, which ensure critical data gets delivered on time. Next, efficiency. It allows less urgent data to be handled without interfering with time sensitive tasks. Next, reliability. So, it can guarantee specific performance level for critical operations. So let us now understand transaction ordering. So what is transaction ordering? So in PCIe, when data travels to the system, they usually need to arrive in the same order they were sent. So this helps maintain the integrity of data and avoids issues like deadlocks. So when the data flow stops entirely or live locks. What do you mean by live loss? When the data keeps circling but never reaches its destination. So, packets within the virtual channel or the lane for the data always follow the order they arrived, unless specific relaxed ordering rules are applied. So, this keeps things organized and avoid conflicts. Next, traffic class. So, the packet with the same traffic class or priority level are routed in order. Packets with different traffic class may not follow the same rules because they don't share an ordering relationship. They are treated independently. So why it matters? So ordering ensure the system operates efficiently without getting stuck or causing error. For example, if a video packet which is a high priority is sent after a regular data packet, the video packet might still be processed first due to its priority, but the system ensure both packet reach their destination without confusion. So let us now understand flow control. So flow control ensures that the system does not send more data than the receiver can handle. So if the receiver's buffer, so here is the buffer as you can see. So it is the storage space for incoming data. And if the receiver buffers are full, the transmitter must wait until there's space available. So how it works? So the receiver has buffers to hold incoming data packets. So these buffer can fill up if too much data arrives too quickly. The receiver constantly updates the transmitter about how much buffer space is available using DLLPs. So the transmitter keep track of this and only sends when there is enough space. So why we use DLLP for updates? So unlike normal TLPs, DLLPs are small and can always be sent even if the receiver's buffer are full. So this ensure updates about available space are never delayed. So flow control is handled entirely by hardware, so software does not need to worry about managing this process. So what are the benefits of having these mechanism? So it prevents data from arriving out of order, maintaining system reliability. Next, it ensures flow control. That means flow data, smooth data flow without overloading the parts of systems. So let us now move to data link layer packets. So why do we need DLLPs? First, TLP error correction. So what is the TLP? So TLP carry the actual data for operations like memory read or write. And next, the error checking process. So each TLP is sent with error detection codes like LCRC. So if the receiver detects an error, it sends a negative acknowledgement back to the sender. The sender replays the TLP from its replay buffer until it gets an ACK or acknowledgement confirming the successful reception. Next, the flow control. So the flow control ensures the sender does not overwhelm the receiver with too much data. So the receiver communicates its buffer availability through small DLLPs. So these DLLP act like tickets that tell the sender you are allowed to send more data now. So the next function of DLLP is power management. So the data link layer also manage power efficiency by communicating power state changes through DLLPs. And let us now understand. So, what is the purpose of DLLP? So, DLLPs are special small packets used for control purposes like acknowledgement and buffer space updates. Buffer space updates of flow control. So, it is 8 bytes and much smaller than TLPs, reducing communication overhead. So these uh, sizes I am telling, it is based on PCI Gen 1 to Gen 3. Uh, and for higher generations, these sizes may change. So, so they only move between neighboring devices and don't propagate through the entire network. And at how does how does assembly and disassembly happens in DLLPs? So at the transmitter, the DLLP is created and a CRC is added. So as you can see, we add a CRC here. It is passed to the physical layer which attach additional frame. You can see here we have added additional frames here and sends it across the link. So it sends across the link and then we work on disassembly. So at the receiver, that physical layer removes the framing info and sends to DLLP. So the data link layer verifies the CRC checksum and for errors and takes appropriate actions. Now let us understand the ACK or negative acknowledgement protocol. So this protocol ensures reliable communication by allowing the sender to retry in case of errors. So the sending TLPs. So the sender keeps a copy of each outgoing TLP in the replay buffer, as you can see here, until it receives the ACK DLLP confirming successful delivery. Then receiving the TLPs. So if the receiver detects no error, it sends an ACK DLLP back to the sender, which detects the TLP from its replay buffer. So if an error is detected, the receiver sends a negative acknowledgement DLP, promoting the sender to resend the TLP from the replay buffer. So how it works? So a DLLP is a small, so it performs important management tasks for the link between two neighboring devices. So the basic structure of DLLP is 4 byte DLLP type field. So as you can see, the DLLP type field is here. So this identifies the type of DLLP and can include additional information depending on the task. And we have 2 byte CRC. So this is a cyclic check redundancy check. So values are added to the packet for error detection. So this is so let us now talk about the physical layer. So the physical layer is the foundation of the PCI architecture because its job is to handle the physical transmission of data over link between devices. So it contains two parts. First, the logical physical layer. So it deals with digital logic to prepare packets for transmission to process incoming data. Next, electrical physical layer. So it handles the actual analog signaling between devices over the PCI lanes.